Hello, this is Mrs. Nearing, and this video is going to be about Bronsted Lowry acids and bases, and we're going to look at some data from the lab that we recently did. So these are some notes from the lab handout which are good to look at as you're trying to write out these reactions that are happening. And our definitions for an acid or base that we're going to be working with, also known as the Bronsted-Lowry definition, is that acids are something that will give a hydrogen to water, and sometimes we call that hydrogen a proton because an H plus cation is basically just a proton. Bases will take a hydrogen from water, and there's some examples of what that'll look like. And when you're writing out these reactions, another thing to keep in mind is you need to make sure that the charge on the left equals the charge on the right. So equations need to be balanced for both mass and charge. Just keep that in mind. So let's look at a couple examples. So we've got these two, acetic acid and citric acid. They're both molecular acids. So the first thing we ask you to do is to go through and think about, is this substance ionic or covalent? So these are both examples of something that's covalent. So let's write out one of them, what would be happening. Let's look at acetic acid. This is vinegar. So it's HC2H3O2. And you stick it in water. And since I can tell from the red color here that it is acting as an acid, that means it is going to be a hydrogen giver. So what that means, when I put acetic acid in water, it is going to give a hydrogen to water. So instead of HC2H3O2, we lose a hydrogen, and it becomes just C2H3O2, and now it's got a negative charge because it lost that positive hydrogen. H2O gained a hydrogen, so now it becomes H3O, and with that hydrogen, it also gained a charge. So notice that the charge on the left is 0, and the charge on the right, is -1 and +1, so it is also 0. So double check to make sure your charges on the sides are equal. And we can also write a K expression for this. So these are all going to be equilibrium reactions with water. So when you write your K expression, it's going to be products on the top. So this is our acetate ion, and then H3O plus. Just so you know, this is also known as the hydronium ion. And on the bottom, we're going to leave out water because water is a pure liquid. Everything else here is aqueous. So the only thing on the bottom is going to be HC2H3O2. And this is a Kc expression because I'm writing it with brackets. We're talking about molarity here. But since this is a Kc expression for an acid, this is known as a Ka expression. So there you go. We've just written our first Ka expression. Okay, let's look at something that is a base. So NH3 is molecular, and when you stick it in water and universal indicator, we should notice that it turns blue. Therefore, it is basic. And based on our definition from our lab notes, we said that bases are hydrogen takers. So let's look at what that would look like. So NH3, you put it in water, it's going to have some sort of equilibrium with water, and it is going to take a hydrogen from water. So my hydrogen is just moving the other direction. So NH3 gains a hydrogen, so it becomes NH4, and with that hydrogen it got a plus charge. And H2O becomes just HO, which we usually write as OH, and it goes from being neutral to being negative. Again, check that our charges add up. So I keep putting my hand there, sorry. And then, so it's 0 on both sides, great. And I can write a K expression for this. So it's NH4 plus and OH minus over NH3. I really should have written states of matter up here. Okay, so my water is a liquid, everything else is going to be AQ. And since this is a Kc expression for a base, you might be able to guess what we call this, and this is called a Kb expression. So we have just written a Ka expression and a Kb expression. Notice they look kind of similar. There's two things on the top, one thing on the bottom. That's a pattern you will notice. So now let's look at some of these ionic compounds. So when you're dealing with an ionic compound, it's important that you split your ionic compound into ions first. So consider like what ions are actually present when you dissolve this in water, and then consider which ion is likely acting as the acid or the base, depending on what pH you noticed. An ion which contains some things to look for. If you notice that your pH is acidic, you're looking for a hydrogen giver. Any ion which contains hydrogen might be a hydrogen giver. If you're looking for a hydrogen taker, then a negative ion is a good candidate because negative things like to stick to positive things. So a negative ion might come along and take an H plus from water. Some ions you'll find are both negative and contain an H plus, so they really could go either way. And in that case, you kind of need to look at the pH of your water and ask yourself, is this thing acting as an acid or a base? So let's look at some examples here. So K2CO3, we see from our data that it's acting as a base. So that means that something in there is a hydrogen taker. But I also want to notice that this is ionic, so it's got a metal, non-metal. So let's look at what the ions are. So when this goes in water, it makes some potassium ions and some carbonate ions. Who is likely to be a hydrogen taker? Well, potassium's positive. Positive and positives don't like to stick together, so it's probably not going to be potassium. So our anion is always a good candidate for being a base, because anions would like to take positive things because they are negative. So let's show our anion interacting with water, and it is going to take a hydrogen. So instead of CO3 2-, it becomes HCO3. And instead of -2, I just added a positive ion to it, so now its charge is going to be -1. And H2O becomes HO, which we write as OH, and it also has a -1 charge. And if you're wondering, like, why didn't I give it 2 hydrogens? Because, CO3 has a -2 charge. Shouldn't I stick 2 hydrogens with it? Well, whenever we're considering these equilibria, we only ever move 1 hydrogen at a time. So we want to consider all of these equilibria separately. And actually, you might notice HCO3-, that actually shows up in a different beaker. When you did NaHCO3, this is baking soda. That's what this is right here. And we notice that this too is also a base. So it can also act as a hydrogen taker. But we consider these as 2 separate equilibria. So we only ever move 1 hydrogen at a time. That is kind of the moral of the story. So move 1 hydrogen at a time. So notice how we're never going to need coefficients in this type of reaction, because all you're ever doing is taking 1 atom from 1 molecule and just giving it to the other molecule or ion. So let's double check that our charges are good. So over here on the left, I've got a -2 and a 0. So my charge is -2 on the left. On the right, I've got -1, -1. So it's -2 on the right. So make sure your charges are equal. And then we can write let's fill in states of matter. So we can write our K expression. So our K expression is going to be products over reactants. So that's HCO3 minus OH minus, and then CO3 2-. And since this is a base, we call this a KB expression. Notice how we're seeing a pattern here. It's 2 things on the top divided by 1 thing on the bottom. You always leave out water because it is a liquid. Okay, so here's another ionic compound which acts as an acid, and this is one of the, this could be a surprising ionic compound because it's made of all non-metals, and NH4 plus is our only example of a polyatomic ion, which is a cation. So usually our cations are metals, but NH4 is an exception. It is a polyatomic cation. All right, so we're looking for an acid, something that's going to be a hydrogen giver. Well, Cl can't be a hydrogen giver. It doesn't have any hydrogens in it, so it must be the NH4. So let's look at the NH4 plus, and we're going to put it in water, and we're going to give a hydrogen to water, and this is an equilibrium. So NH4 becomes NH3, and it loses that positive sign. Where does that positive go? It goes over here to the water. Okay, and then these are all aqueous. My water is a liquid. So if I write a K expression here, I'm going to call it Ka because it's an acid, and NH3, H3O plus, and then NH4 goes on the bottom. I don't know if you notice anything that looks familiar here. NH3 is actually a base that we just dealt with a little bit ago. So this thing right here that was made during this reaction is a base. And the thing that is made after an acid gives a hydrogen to water, the thing that is left over is something known as the conjugate base. So we'll talk more about that later. Okay, here's another one. We've got an ionic compound acting as a base. This one threw some people off as to what the ions are. So if you look at what happens here, I've got my metal ion, so I've got 2 sodium ions. And what's left? This thing right here, this thing must be my polyatomic ion, HPO4. Remember, we memorized the list of polyatomic ions, but we just memorized a very small list. There might be other ones you'll encounter. And you might say, well, how do I know the charge of this thing? I've never heard of it before. Well, it takes 2 sodiums to neutralize the charge of one of these things, so this thing must have a charge of -2. Okay? And I'm looking for a base. I'm looking for a hydrogen taker. So positive things are not likely to take another positive thing. So my anions are my likely hydrogen takers. So HPO4, -2. I'm going to add this to water, take a hydrogen from it. I now end up with H2PO4. And my charge, let's do a quick charge tally here. I'm gaining 1 positive, so I become -1. Okay. Water loses a hydrogen, becoming negative. If I write my K expression, we call this a KB. And I'm using brackets because we're talking molarity here. And we leave out H2O because it is a liquid. All right. And here is a very similar looking compound with just a different number of sodiums and hydrogens here. Whoops. I think I actually wrote the formula here wrong. Okay, I was confused for a minute. Okay, this is the wrong formula. This should be NaH2PO4. This thing right here acts as a base. We just saw that. And this thing right here acts as an acid. So let's first, it's an ionic compound, so let's look at what the ions are. So I've got sodium and I've got H2PO4. Well, this thing must have a charge of -1 because it takes 1 sodium to neutralize it. I am looking for an acid, so I'm looking for a hydrogen giver. So can sodium give hydrogens? Nope. So notice that are these guys right here, the spectators, the ones we've been crossing out, are our usual suspects that were the spectators when we did like precipitation reactions. So when you see your alkali metals, when you see nitrate, when you see your chloride ions, those ones that are typically spectators that are always soluble, the same thing happens in acid-base reactions. These same ions tend to be your spectators. So let's look here. We've got H2PO4 minus and H2O. So here's an ion where it contains hydrogen and it's negative, so it could either give a hydrogen to water or take a hydrogen from water. And how do we know what it does? Well, we just look up here at our data, and we can see from our data that it is in fact acidic. So that tells us this ion must be giving a hydrogen to water. So it goes from H2PO4 to just HPO4, and then H2O becomes H3O, and there is our reaction. So charge on the left is, we've got -1 plus 0, so we got -1 on the left, and then -2 plus 1, it's -1 on the right. So we are all set with charge. I'm going to call this a Ka expression because it was acting as an acid. So on the top are my products. Remember we said before, H3O plus, we call this thing the hydronium ion. We'll come back to that language later. And then H2PO4 minus is on the bottom. There was one example in the lab of a substance, an ionic substance that was neutral. So when you put this in water, you end up with K plus ions and Cl minus ions. And we know this substance is neutral from our data, so that means no one is either giving or taking hydrogens, which kind of makes sense if you look at what these ions are. These are some of our classic spectator ions we were just talking about. So your alkali metal compounds tend to not stick to anything. They tend to just be spectators. Your chloride ions tend to not stick to anything. The only time you'll see your chloride reacting with something is if you stick it with silver, lead, or mercury. It would form a precipitate, but apart from those examples, it's going to be a spectator. So what is really happening in what is really determining the pH in the solution is it's just the dissociation of water. So you've got your liquid water dissociating to make H plus ions and hydroxide ions. The K expression for this is just H plus and OH minus, so we call this KW, and we know the value of this at room temperature is 10 to the negative 14, and that's why we end up with a pH of 7 here. So yeah, basically your potassium chloride, they're just spectators, they're not doing anything. All right, and that's it for our slides here. Let me know if you have any questions.